So good morning, everyone. Welcome back. So today we have Professor Arpan Kabiraj from IIT-Palakkad. So he'll be speaking today on generation of this mapping class group. Yeah, Arpan, over to you.
Thank you, Sir Abhijit. So today I'm going to talk about generators of mapping class group. Okay. So the setup is you must have heard about the definition of what mapping class group is, why it is important, and so on and so forth. So today we are going to prove one important property, namely that mapping class group is finitely generated. Okay. In fact, it is actually finitely presented, but I'm not sure whether I will be able to go up to the presentations of mapping class group. So today we will focus finite generation of mapping class group. So this theorem was first proved by Max Den in 1920s, and he sort of first proved it for punctured spheres and then used Lewin argument to prove this result. Licorice gave a proof around 1960s, 1970s independently, and sort of the Licorice's idea later turned out was already sort of similar to what Den has done, but Licorice was unknown to that idea because Den's paper, this particular paper was not that popular at that time. Okay. So we will not follow either Den or Licorice's argument because that is basically case by case technical proof. So we will use some other method to prove this theorem. So let me write down the theorem. So let me complete this statement. Put non-separating simply closed first. Okay. So the statement is the following. Assume your genus is greater than equal to 0. And for this discussion, we will pretty much assume genus is greater than equal to 1 or genus is greater than equal to 2. Then the mapping class group mod of SG, I will use this notation for mapping class group. Mod means mapping class group. So the mapping class group of a closed surface is finitely generated. And not only that, you know exactly what the generators are. It is actually generated by finitely many Den twists about non-separating simple clusters. Okay. So let us focus on the statement once again and let us discuss what are the meaning of the terms. Okay. So you have seen the definition of mod SG. Let me remind you what it is. Yeah, any questions? By the way, if you have any questions or doubts or anything, you just stop me and ask, no problem. Okay. So what are the objects here? So we have mapping class group, which is homeomorphisms, orientation preserving homeomorphisms, which acts on the surface and which is our identity on the boundary, which fixes the boundary point-wise, modulo isotopes of S, which fixes the boundary point-wise. Okay. So this is pretty much the definition of mod SG. Again, so here, let me write S rather than SG because here I am assuming surface might have boundary. Okay. So this is the definition of mapping class group. It's the isotopy classes of orientation preserving homeomorphisms, which are identity on when restricted to boundary. And throughout this isotopes, we are also fixing the boundary. We are not moving the boundary. Boundaries are point-wise fixed. These are the things you have to keep in mind for today's lecture. This is a slight technical detail. Okay. Now, so this is the first unknown term here. Finitely generated means it's a group which is generated by finitely many elements. So there are finitely many elements in the group G1, G2, Gk, which generates the whole group. Den twist you must have seen already. So how does it look like? So you have a curve alpha. Let's say this is your curve A, and this is let me put better picture. So suppose this is your curve A and you have another curve B, call this B. So you apply P of A on B and you either take left twist or right twist. So we will call the left dent twist as dent twist. So you go like this. So let me remove this part. So you go like this, come back, and this is PA of. So dent twist can be understood as a map acting on the curve. At each simple closed curve, at the closed curve where you are taking the twist, you are basically twisting the surface. You are holding it as a neck and you are twisting it. That's why it's called dent twist. Okay. So this is the definition of, this is the description of dent twist. It's not exactly the definition. For the definition, you have to take a nebular neighborhood of A and you have to put a homeomorphism in the surface and you have to define it accordingly. Okay. So this is the definition of dent twist. Okay. What is a non-separating simple closed curve? Well, given a simple closed curve means a curve which do not have any self-intersection. Okay. So a simple closed curve simply means it's an embedded curve. Okay. So what is a non-separating simple closed curve? Okay. Given any simple closed curve, there are two possibilities. If you delete the simple closed curve, the surface either remains connected or it becomes disconnected. There are two options. Take a simple closed curve, cut your surface. There are two possibilities. Either the surface becomes disconnected or it remains connected. If it remains connected, we call it non-separating because it's not separating the surface. If it becomes disconnected, we call it separating. Okay. So non-separating means if you cut the surface along the curve, the surface still remains connected. So here is an example. So this is your genus to surface. This is an example of separating simple closed curve. If you cut along the green curve, the surface becomes disconnected. And this is an example of non-separating simple closed curve. So if you cut along the blue curve, the surface still remains connected. Okay. So these are the terminologies and this is the statement. Any questions or doubts? Okay. So there is also a bound on number of generators, number of dent twist generators that you might need. In this case, there are other restrictions. There are even more stronger version of this theorem. But this is the general theorem, and this is what we are going to prove. At least we will try to give you some ideas of how the proof works. Okay. Now, before going into that, there are two things here. So, firstly, why we cared about mapping class group? What's the reason people are interested in mapping class group? And the second thing is why this property is important. Well, the first, you might have seen some version of both of these answers. So let me give you the second answer first. If you have a finitely generated group, then you can start with one of its finite generating sets, and then you can basically quantify in a finite space the description of the group, meaning you can feed it to a computer. It's the easiest way to understand why people are really interested in finitely generated group. You can just put the generators, you can put the generators of the group and you can describe the group. Even better, actually finitely presented. Your group is finitely presented. You put the generators, you put the relation. So you can describe the group to a computer. So in a finite time, you can compute the certain properties of the group. That's why finitely generated or finitely presented groups are important. And this mapping class group is indeed finitely presented, that we will see in the later part. Okay, that's the first thing. Why people are interested in mapping class group? Okay, so let me give you some brief kind of idea. So one fundamental question with the early of 20th century was classification of three manifolds. Okay, so we know classification of surfaces, classification of two manifolds. Okay, so we have classified everything uh, up to compact, close, connected surfaces. We know they are completely classified by genuses. So that was a classification of two manifold, and people were interested. What are the classification of three manifolds? Now, you know, in dimension 2, if your genus is greater than equal to 2, all the manifolds admit a hyperbolic metric. So another way to say this is most of the manifolds in dimension 2 are hyperbolic. Okay, hyperbolic means it admits a constant sectional curvature -1. Now, this was sort of a general guess or a kind of idea that, okay, there is a possibility that this might be true. Whatever it means to say that, okay, most of them are, also it might, there is some truth to, there might be some version of this fact which might be true for three manifold also. There was a concept like that for three manifold. Okay. So the first question is, how do you create hyperbolic three manifolds? That was the first question. To claim something like, okay, there are enough number of hyperbolic three manifold, you have to first give some examples. You have to construct some three manifolds. Okay. So how do you construct non-trivial closed three manifolds? Okay, hyperbolic three manifolds. So here is the process you do. So take a surface of genus G greater than equal to 2, closed surface. Take a homeomorphism of the surface and you do this construction. Take SG cross 0, 1. So suppose this is your SG. Take the product of SG with itself, cross it with 0, 1. Okay. Then you glue this section from top to bottom by the map phi. Okay. So you quotient it by phi. Okay. This is called the mapping torus. Is the construction clear? Take the surface, take surface product the interval, then glue it. But don't glue it using identity, glue it using the homeomorphism phi. That gives you a three manifold, a closed three manifold. This do not have any bound. This gives you a closed three manifold. Well, now the thing is, this is a classical result, and you can actually try to prove that if. So now the fact is the following: if phi is isotopic to C, if you have two homeomorphisms phi and C, they are isotopic, then M phi is homeomorphic to MC. Okay. So if two homeomorphisms are isotopic, then the three manifold that you are going to get be homeomorphic. So this means that ultimately, if you by this construction, if you want to construct closed three manifolds using this construction, using this closing method, all you have to know is isotopic classes of homeomorphisms of surfaces, and that is what exactly mapping class group is. So another way to say why people are interested in mapping class group is to tell you how many different mapping torus can be there in the three manifold category. Start with the surface, you construct a three manifold by taking a mapping torus. How many different closed manifold you can construct? Well, as many as mapping classes are there. Yeah, Neeraj, go ahead. Please go
ahead. So what you said is like how many mapping tori is depend upon the how many mapping classes is not required the converse of this statement. that if you take a two mapping torides, then they are homomorphic if and only if their gluing map is.
I don't think so. I don't think so. I don't think
Okay.
so.
Is
So I have to check,
that
but
statement is any chance true? Okay.
There was one restriction you needed. I think there is one restriction in needed. I cannot recall it out of my head, but I don't think directly it will be true. But some weaker version of this thing is true. That now I recall. Yeah.
Okay. Thanks.
Okay. Yeah. Any other questions? Okay. So now, yes. So now the question. So let's go back to the original question. Now we have enough closed three manifolds. We have seen at least some class of three manifolds, and these three manifolds come from each mapping classes. So if you know what the mapping class, what are the elements of mapping class group look like, you know how many different these three manifolds are. Now the original question was, okay, what happens to hyperbolic manifold? These are examples of closed hyperbolic three manifold. And this was the first step of what is called geometrization conjecture. Thurston proved that if your phi is of some particular type, and this particular type of map is called pseudo-Anosov, then this manifold is indeed hyperbolic. So just by looking at this homeomorphism, this isotopic class of homeomorphism, you can tell whether this manifold is hyperbolic or not. And this is what Thurston's geometrization program was at the beginning. Look at the elements of mapping class group, and you give an algebraic or topological classification of mapping class group. Don't go into three manifolds, just mapping class group and its action on the surface, and you can determine whether this three manifolds is hyperbolic or not. So mapping class group elements can be classified into three types: finite order elements, reducible element, and pseudo-Anosov. And so finite order and reducible can intersect, meaning there are finite order reducible elements which are also finite order and vice versa. But they are mutually exclusive with the pseudo-Anosov. So this is the example of why people were interested in studying mapping classes. It's basically to understand what happened to this mapping class, what happened to this closed three mapping. Okay, so this is the sort of the motivation behind why people were interested in mapping classes. Okay. Now, let me go back to the theory. How do you prove such a theorem? How do you proceed to prove that such a theorem is true? Before going into that, let me describe something for you. So suppose if Gn is a surface which has genus G and n punctures. So what do I mean by punctures? You take any n points and remove them. Just the point. Delete the point from the surface. That is called punctures. Okay. So when you talk about mapping class group of such a surface, what you do is you consider homeomorphisms. Now just assume that the surface do not have boundary as of now. Orientation preserving homeomorphisms of this quotient by isotopic classes of homeomorphisms. This. So in this definition, what you are allowed is you can permute the punctures. So suppose you have a sphere with, let's say, k punctures. So in the mapping class group, you are allowed to permute the puncture. You can go from here to here, or you can take this puncture to this puncture to this puncture, just by moving it. Okay, that is allowed. So the point is, if you look at dent twist, if you just look at dent twists are defined over some curve, some non-separating curve, which is lying inside the surface. No matter how much you twist along a curve, you will never be able to permute the punctures. So if we are looking at punctured surface, this theorem is simply not true. Because as I said, elements of mapping class group of a surface with punctures are allowed to permute the punctures. But no matter what you do with the dent twist, it can never permute a puncture. Okay, so we have to put some restriction. if I want to extend this theorem for punctured surfaces. Okay. So the restriction is, what you do is you fix the punctures. So this is called pure mapping class group. What is a pure mapping class group? The pure mapping class group, this is a subgroup of mapping class group which fixes the punctures pointwise. Okay. So once you define this, there is not much difference between a puncture and boundary, because mapping class group, elements of mapping class group were not allowed to change the boundary points. They were supposed to be identity on the boundary, and now you are fixing the punctures, so you are also not allowed to change the punctures. So in this definition, in this pure mapping class group category, there is no difference between a surface with puncture or surface with boundary. You can think of surface with puncture or surface with boundary. They behave like same, except with one slight problem, and this is the problem that I would like to mention. Suppose you have a surface which is something like this. Now, take a simple closed curve which is homotopic to boundary. Call it something D. Now, if you look at dent twist along D, this is actually a non-trivial element of mapping class group. Non-trivial in mod S. So this is. However, if you look at the same surface and except punctures, except boundary, now you have a puncture. Now this curve is actually homotopically trivial. The point is, if you twist it and the twist goes to the puncture, you can slowly untwist it. So the moment you go towards the cone, towards this point, the twisting become untwisted, just reverse itself. Okay. So this is a slight difference that you have to keep in mind in terms of punctures and boundaries. So when you have a boundary, if you take a dent twist along the boundary, that's a non-trivial element. That's a non-trivial element of your mapping class group. Okay. However, if you take the boundary and fill it, so think of this part, think of going from here to here as adding a punctured disc here. Just take a disc with a puncture and you glue it to the boundary. Okay. So if you glue it with punctured disc to the boundary, this vanishes. Okay. Just keep that in mind. So in our proof, we will use first of all pure mapping class group of punctured surfaces, and we'll use this fact that when I glue a punctured disc to a boundary, what I essentially do is I'm killing a dent twist along the boundary curve. Okay. So if I just take this map, which takes mapping class group of bounded surface to mapping class group of this punctured surface, this dent twist will be in the kernel. So this is called capping homomorphism. I will come back to it later. Come back to this. Okay. Any questions?
This theorem is true for genus D surface with boundaries or no?
Can you repeat this statement?
So this theorem is true for genus G surface with boundaries?
This theorem means which one?
Above one, which you have stated.
So this theorem is true for, yes, you are right. It's this theorem is true for genus G surfaces with boundaries, except with one slight change. Here you have to add the dent twist along the boundary curves.
Okay.
Okay, because you understand the reason, right? So along the boundary, you cannot do much things, right? Okay. Is it clear?
Yes, thank you.
Okay. Yeah. And this theorem is also true for pure mapping class group with punctures also. Because there you don't have to worry about the boundary curves, because anyway, everything goes to, this becomes trivial. This becomes trivial. Okay. Any other questions? Okay. So first what we will prove is the following. If you have a pure mapping class group of a surface with finitely many punctures and without any boundaries, then that group is finitely generated. That is the first thing that we are going to prove. Okay. So how do we prove such a theorem? How do we prove this kind of theorem? Okay. So let me sort of give you the motivation, and then we will follow step-by-step procedure how to prove this theorem. Okay. So what is the result that we are actually going to prove? We are going to prove that mapping class group of a surface of genus G with n punctures, this thing is finitely generated. Okay. This is what we are going to prove. So here we will assume G is greater than equal to 1, n is greater than equal to 0. Okay. So whenever we have a kind of a result where we want to show that a group is finitely generated or finitely presented, what are the techniques that we know that proves a group is finitely generated or finitely presented? Can you remember any result that you have seen so far in your course or in this discussion sessions or in the talks where you prove a group is finitely generated or finitely presented?
Millar's.
Miller's-Bach type. Thank you. So this is the typical way of proving a group is finitely generated or finitely presented, is you choose a group G, and if you want to show it's finitely generated or finitely presented, you find a space X on which it acts nicely, and I will specify what nicely means, so that the quotient has some kind of finiteness property. Either the quotient is compact, or quotient is a finite dimensional simplicial complex, or it's a compact manifold or something. These are the three essential tools to prove a group is finitely generated. The first one is you find a space on which the group acts nicely. Secondly, the space on which it acts nicely must have some kind of structure. So in Miller's-Bach lemma, it must have a path metric. So it should be a path connected metric space. And the third one is the quotient should have some kind of finiteness property. Okay. In Miller's-Bach, the quotient is compact. Okay. This is actually, if you have seen the proof of Miller's-Bach lemma, the first part of Miller's-Bach lemma, where you prove that the group is finitely presented, that part is not hard. The hard part of Miller's-Bach lemma is actually to show that the group is quasi-isometric to the metric space. That's the hard part. So this result that a group acts on a space and the quotient has some finite property implies the group is finitely presented. This is in general true in a more general context. Okay. So you can start with some arbitrary group and you can take X to be a simplicial complex. And if your group acts on the simplicial complex with certain property and the quotient is finite simplicial complex, then also group is presented. So that's the first step that we are going to need here. So we have to find some space on which this acts. This is the first property. Okay. Second thing, the first first one is let me write it down. Find a space, find a nice space on which mod SGN acts nicely. That's the first. Okay. Second part is, and this is the second step, this is also interesting, use induction So on G and S. Okay, so the first part is sort of you have seen so far. It's the Milner's-Watt lemma. Now I will come to the specific problem, this one, where we have to use the induction on G on. Okay. So what kind of result that we sort of use to give this proof of induction? So here is the idea, and this is sort of going to be the crux idea here. So let me clearly write this one. So the idea is the following. So the first thing is we will use induction on genus. So there is two-step induction. One is on genus, one is on just. So first step is use induction of genus. Okay. So for low genus surfaces, we know that the mapping class group is trivial. So for example, if you take a size punctured sphere, that you must have seen that the mapping class group is trivial. I think this has been done already. This is called Alexander trick. If you have a thrice punctured sphere, then the mapping class group is trivial. So that's our base point. Or even a torus with a puncture, the mapping class group is trivial. These two will be our base point, S03 and S11. These two are our bases. So now let's see how we use the induction on genus. So suppose you take an element. So this is again, let me remind you, you were lost a bit. This is what we are going to prove. We're going to prove mapping class group is finitely generated, and it's finitely generated by den twist along non-separating simple cluster. So to prove that, first we are going to prove that this is finitely generated. If your surface has some punctures, and if you take the mapping class groups which do not shuffle the punctures, then this is also finitely generated with the same set of generators. Okay. So for that, first you have to find a space on which it acts, and then second, you use the induction. So now my claim is that this induction will tell you what is the space that we have to consider to see a nice action. So let's see how we prove about any of this kind of result. So take a mapping class group from surface of genus G with n punctures. Okay. And then we have to somehow reduce F to we have to somehow modify F to get a element of mapping class group of a surface which has one genus less, and then we can use the induction. Okay. So we have to cook up using F. We have to somehow cook up a homeomorphism which reduces the genus. Okay. And this is the important part that I want you people to know, that this is why this non-separating thing comes into picture. Because if you look at simply this picture, if you remove a non-separating simple closed curve, your genus goes down. Is this thing clear? If you remove a non-separating closed curve, you obtain a surface which has less number of genus, more number of boundary components, but genus goes down. Is the motivation clear why we are using non-separating simple closed curve? If you remove non-separating simple closed curve, the genus goes down. So you can use induction. Okay. So now I have a mapping class F, and I choose any non-separating simple closed curve. A is any non-separating simple closed curve. Okay. So now if F fixes A, you are done. You remove A, then F will induce a homeomorphism. It will give you a mapping class group of S minus A. So your genus reduces, you are done. But that is in general not true. There are a lot of mapping classes which does not fix any non-separating simple closed curve, any simple closed curve at all. Okay, and this is one of the these are the interesting examples which gives you hyperbolic structure here. So the hyperbolic structure comes from homeomorphism, which does not fix any simple cluster. These are the pseudo anisotropy. Okay. So our first problem is F does not fix A. Well, can we cook up something using dent twist so that if I compose it with F, then it fixes it? That's our next process. Okay. We have to use something that we know. Okay. So let's see. So consider FA. This is a non-separating simple closed curve. Consider A. This is also a non-separating simple closed curve. Can you find a homeomorphism which takes FA to A? Remember, FA is a non-separating curve. A is also a non-separating curve. Is there a homeomorphism which takes FA to A? Just orientation preserving homeomorphism. Any guesses?
So we have seen that topologically there is only one non-separating simple closed curve.
Right, exactly. Thank you. So topologically, there is only one non-separating simple closed curve. That means if you remove FA from the surface, you are going to get a surface of genus G minus 1 and with n minus 2 boundary components. If you remove A from the surface, again you are going to get a surface S which is of genus G minus 1 and boundary n minus 2. So these two are homeomorphic. So there is a homeomorphism which takes FA to A, which, as Praveen said, is similar to saying that up to topology there is only one non-separating simple closed curve. So we do have a orientation preserving homeomorphism which takes FA to A. Well, that's at least sanity check. We know that there is a homeomorphism which takes FA. Now, can we construct a homeomorphism which is a composition of dent twist which takes FA to A? Okay. And to do that, so let me write down the question. So there exists a homeomorphism H such that H of FA is equal to A. So now the question is, can we construct such an H using dent twist? Okay. So what happens if we can prove that H is, if you can construct H as a product of dent twist, then what will happen? H composition F will take A to A. So if I have such an H, then H of FA is equal to A. So therefore H composition F is a homeomorphism on the surface minus A. So that goes down one genus. This is a product of dent twist, so F will also be a product of dent twist. H of F is a lower genus surface. H of F is a homeomorphism on a lower genus surface. You use induction. So H of F can be written as a finitely many product of dent twist around non-separating simple cluster. H, if you are lucky enough, H can be written as a product of dent twist of finitely many non-separating cluster. But just for starters, assume finitely many product of dent twist. Then you take the H inverse, and F can be written as a product of finitely many dent twist. So that will be your okay. So is the question clear here that what we are going to achieve here? We are going to construct a homeomorphism which takes FA to A and not any other homeomorphism, a homeomorphism which can be written as a product of dent twist.
So we'll get exactly that homeomorphism or up to isotopy?
We see here, I don't need isotopy. I just need one homeomorphism. I want to write F as a product of something. So if H composition F is a product of something, I take H inverse. This will again be some composition of dent twist, and I will be done. Okay, as long as it is finitely manipulable. Is it okay? Yeah. Any other questions? Okay. So now let us see. So this is as good as it sounds, because if it sounds too good, it is too good to be true, and this is indeed the case. In general, we might not. But let us see, what do we know about dentistry? Let us see what are the results that we know about dentistry. So let me go a little bit, let me tell you a result about dentistry. So here is a fact, and this fact I will prove. This is just 4 pictures. If you have 2 curves, A and B, 2 simple closed curves. Then this gives you sort of what is known as the braid relation, but yeah, don't bother about that. So the result is the following: TB, TA, TB of A is equal to B. So if you apply the dent twist along B to A, and then again apply the dent twist along A to that final result, you are going to get. And have you seen this result, by the way?
So you missed the hypothesis, right? This geometric intersection should be 1.
Sorry. Right. Thanks. Right. That's the important part. Sorry. Correct. Thank you very much. If the geometric intersection is 1, right? This is the important part. Sorry, I missed that. Yeah. Have you seen this result?
Yes, I mean, very beginning lectures.
Okay. So this has been proved. Okay, good. So now let us look at this case now. I want H which takes FA to A. Okay. So so there is case 1. So there is case 1. Suppose geometric intersection of FA and A is 1. Now this is going to play a very, very huge role. So then, by this fact, this implies that if you apply the dent twist P of FA, this will take. So this is my H.
Sorry, but in
sorry.
other order.
Yeah, FA. Sorry, this is FA. Let me write it. Okay. So is this clear? First, this can be taken as H. If intersection of FA and A is 1. Is this clear? Any question? So this I will take as A, H. H is a composition of just 2 dent twists, and this I will take as H. But this is with a huge condition that geometric intersection of FA of A should be 1. Now, earlier FA and A might not even be related. Now we have some conditions that we can work on. Okay. But what is geometric intersection number of FA and A is not 1. So case 2, what if geometric intersection number of FA and A is, let's say, n, which is and this is where the fundamental observation comes from, and this was actually, firstly, this was due to Harvey, and before that it was pretty much known, but this is formalize Harvey. There was other reasons also for introducing this complex. So the idea is the following. If the geometric intersection number between FA and A is 1, we are done. If the geometric intersection number of FA and A is n, you construct a sequence from A to FA such that at each stage you get geometric intersection number 1. So then, and this is sort of the important fact, there exists a sequence of simple closed curves which start with A equal to C1, sequence C1 to Cn, which start with sequence C1, ends at F1, such that geometric intersection number of IC and CR is 1 is equal to 1. Every time, you may not go from A to FA directly, but there is always a sequence of simple closed curves. Each time, you can go from one to the next just by doing self-intersection number 1. And now you use these three facts combined to write to get this H. So from here, you will get H1, H2, Hn, composition F. That will be a lower genus surface, so F will be H inverse of this. Is this clear? Now this proves, so this, depending on your F, this length of the sequence can increase. So this actually in a sense proves to you that every element can be written as a product of den twist, not necessarily finitely many, but at least product of den twist. So the den twist generates the mapping class group, not necessarily finitely, it generates the mapping class group. For finiteness, we need something else. So is the genus induction clear? Is the idea clear? Why we are using this? Any questions? So now if you look at this fact, what do you have to do to prove this fact? Well, one way to prove this fact is the following. This is where the idea of curve complex comes into picture. You consider a simplicial complex, a graph, forget about simplicial, simply a graph whose vertices are simple closed curves. And you join two simple closed curves, join two vertex if their geometric intersection number is 1. So what this fact is saying is that this graph is connected. Let me write it. So consider a graph whose vertices are simple closed curves, homotopy class, isotopy classes of simple closed curves, and edges are given by the following: Vi and Vj are connected by an edge if geometric intersection number of Vi and Vj is equal to 1. Okay. So you construct this graph whose vertices are isotopy classes of simple closed curve, and edges are given by pair of vertices whose geometric intersection number is 1. Then this fact is simply says that, call this graph G, then this is G is connected. This fact is same as saying G is connected. Is it clear? If G is connected, that means you can go from one vertex to another vertex by going through a bunch of edges, and each edge gives you another simple closed curve, which is geometric intersection number 1. So you can go from here to here just by this. Now, if you look at this space, mapping class group acts on this. This is just vertices are simple closed curve, isotropy class of simple closed curve, and each mapping class takes a simple closed curve to another simple closed curve. So this acts on this graph.
So what
This
about
is-
intersection number 0?
That I've come. So first we are focusing on geometric intersection number 1. Okay. So this is the motivation why I'm saying that why we are interested in geometric intersection number at all or curve complex at all. Okay.
Okay. First of all, we just assume that FA and A has a geometric intersection number greater or equal to 1. That's the case.
Right. We are assuming first the geometric intersection number of FA and A is greater than equal. If it is 0, then we we can't do much thing. So if FA and A has geometric intersection number 0, so then we have to go somewhere, right? You have to find some curve which has geometric intersection number 1 if A, then take another curve. So this we can follow. This doesn't need n greater than equal to. This is actually we can sort of remove
So this graph we are considering, this will be connected, disconnected if I.
Yeah, this graph is connected. That's what I'm saying.
So if I consider two vertices as, geometric intersection number 0.
Geometric intersection number is 0 or 1.
0. Suppose I have taken two vertices and they have geometric intersection number 0. Will we be able to connect them?
Yes,
we have seen that it is, if it is greater than something, then we can connect it by this sequence, right?
Right. Yeah, we will be able to connect. No problem. Okay. So we will come to the bigger one. So this is just a motivation. So if we consider such a graph, then this can be connected. Okay. This is sort of the point here. It can be connected. This is the first point.
Okay.
Unfortunately, as you pointed out, in this generality, if we consider all simple closed curve, this is actually not true. There is a problem. If you consider this curve, you may not be able to go from FA to FA just by taking geometric intersection number 1. So I haven't proved anything. I'm just telling you what is the motivation. Okay. So now, so we have understood that, okay, if I consider a graph whose vertices are sort of simple closed curve and edges are determined by some kind of geometric intersection number relation, then this will give me this kind of result going from A to FA. So this was the part of the motivation of defining a graph whose vertices are simple closed curves and edges are given by some kind of intersection relation between them. Okay. Now, in this generality, this result is not true, as it is stated here. If I take all the, okay, so we need some kind of refinement. Okay, so that's the first thing. This sort of gives you an idea what type of space we are going to consider on which mapping class group acts. The vertices are going to be a bunch of simple closed curve, isotropy class of simple closed curve, and edges will be determined by some kind of relation which comes from geometric intersection number between. That's the first motivation. Okay. So this is about, yeah. So any questions so far? Okay. So now this is about this induction on genus. Yeah. Any question?
Yeah, I'm sorry, but I'm little confused in the fact.
Yeah.
Is it hidden assumption that this curve in this green line that these all curves are non-separating?
I have to put that condition. You're absolutely. That is the condition I have to put. Actually.
Okay.
That's the condition. Otherwise, I won't be able to put. That's the condition I have. That's what I'm saying. That this exactly as it is stated is not true. We have to use that fact. Yeah, you're right. So that you need see here. FA is non-separating, A is non-separating. So that's the fact we need to have. Yeah, sure. Right. Okay.
No, I didn't get. For connectedness, you want non-separating or what?
For connectedness with this relation, I want non-separating. If I want disjoint, the edges to be disjoint closed curves. If I just take curve complex, that is connected. No problem. You take all simple closed curve, and the edges are denoted by pair of curves which has intersection number 0, then it's correct. But if I want 1, I have to put the non-separating condition. Okay. This is special about non-separating. Okay. Any questions? Hello. Okay. Yeah. Am I audible?
Yes.
Yeah.
Okay. Okay. So now, this is just to motivate you what is coming next. Okay. So this is the first part, which is sort of telling us that we have to consider a graph whose vertices has some classes of simple closed curve and edges are defined by some sort of image. Okay. So this is about just induction on genus G. Next step is induction on N. Okay. So this, let me just write it down. So this motivates to consider curve complex, and I will introduce what curve complex is. So this is the first motivation. Okay. Now comes the second part, the induction on punctures, and this is the second motivation. So what happens if you take a mapping class group, pure mapping class group, which does not shuffle the puncture of a surface with genus G and N punctures, and suppose you fill up the puncture, you forget about the puncture. Suppose you have a surface here, some surface, and it has a bunch of punctures. Now, every homeomorphism of this surface fixes this punctures pointwise. Now, if you remove this puncture, if you take a homeomorphism of this surface with 4 punctures, we call it F, and if you remove this puncture, it will still be a homeomorphism of the surface, right? So every homeomorphism of a surface with n puncture is also a homeomorphism with surface with n minus 1 puncture. That's not a problem. That is perfectly all right. So every time I have a map which takes a homeomorphism with surface with n punctures to a homeomorphism with surface with n minus 1 puncture. However, here is the problem. If you have a curve which is like this, let me color code it differently, and you take a dent twist along this blue curve, this is non-trivial in this surface with 4 punctures. But what happens is, if you delete this puncture, sorry, oh my God. So anyway, I have to use, if you delete this puncture, suddenly this curves become inessential. This curve is homotopic to puncture. So the dent twist become trivial, right? So this map, which takes a homeomorphism of surface with n puncture, surface with n minus 1 puncture, has something in the kernel. There are some curves which becomes trivial in the homeomorphism. Okay. And so the question is, so there is a well-defined homeomorphism here. Call it phi, or let me check what is the notation they have used. I will pretty much use the same. Okay, so they have used forget. So let me write this. So let me write this. So this is for forget. So forget map means you simply forget that there is a puncture. Okay. So question is, what is the kernel of forget map? This is going to give you a homomorphism between these two groups. So if we can find what is in the kernel, then we can use the induction on punctures now. So here, if you look carefully, we have reduced the number of punctures from n, we went to n minus 1. So if you can understand what the kernel is, we can use the induction on this thing. And this is the second part of the second most important thing. This is called Berman exact sequence. And so what is Berman exact sequence? So the Berman exact sequence says, let me write it down. If you look at the mapping class group of surface of genus G with n punctures, so let's say plus 1 punctures, and you forget the puncture, forget one of the puncture at a time, then the kernel, so this is again, this part is not hard. The kernel is exactly the fundamental group of surface genus. And this gives you an exact sequence. So this is called Berman exact sequence. So Berman tells you exactly what the kernel is. Okay. Not only that, you actually know what this map is, and this is actually the most important part. This thing was already known. What Berman gives you is what this map looks like. Can you understand this map geometrically or topologically? So Berman proved that these elements of this kernel can be identified with the elements of fundamental group. And when you look at this image here, this will be nothing but, if you take a curve here alpha, this will be a product of dent twist with a bunch of curves which looks similar to alpha. So this is called a push map. Okay, so I will explain what this push map is, but this is the second important. Okay, so Berman tells you exactly what this kernel is, and this kernel map sits inside this pure mapping class group as a product of bunch of dent twist along some non-separating simple closed curve. So here we will use induction in this step. This will give you an induction of M. In the last curve complex setup, we will use induction on genus G, and these two together will give us this fact that mod SGN is finitely generated with finitely many dent twists along non-separating simple closed curve. So the first step tells you which space it acts. Then you use the induction on G, and this sort of uses this part. And then you use induction of N, and to use induction of N, you need Berman exact sequence. Okay, any questions? So now I will go into each of these topics. I will first define what curve complex is. Then I will go to the connectivity of curve complex. Then I will go to the non-separating curve complex. And then I will show that non-separating curve complex is connected. Then I will go to the Berman exact sequence. And then I will put together to give you the proof of this. Okay. Any questions so far? Okay. So maybe let me introduce what is curve complex. This is now these topics are itself important. These objects are important in themselves, and I will sort of in between I will tell you why they are important, why people actually bothered about the curve complex and stuff like that. It's not just it is used to prove this result only, has its own independence important. And so these things, and Berman exact sequence is very, very important. It uses much more. It is used in a lot more than you can think of. So let me start with curve complex, which is very, very simple object. So curve complex. So consider a simplicial complex. So let me start with. So let me start with the fact that if you have a surface, so Let S be a surface. So you start with any surface, any simple closed surface, which may have boundary, may not have boundary, or whatever kind of surface you want. Okay. And then you choose the following. So what are the vertices of this complex or the simplicial complex? The vertices are isotopy classes sorry, of simple closed curves. And there is one thing I would like to put here. Please keep that in mind. Essential. Okay. So what do I mean by essential? This means the simple closed curve is not homotopic to boundary or not homotopic to puncture. So we are not considering curves which are homotopic to the boundary curve or homotopic to puncture curve. Okay, is this clear? This is a technical point, just keep in mind. The reason is basically if you have a boundary curve of, there's one boundary curve and another, so if your surface has two boundaries and take these two boundary curves, you cannot go from one boundary curve by another boundary curve by any kind of intersection relation. There is no other simple closed curve which basically hits the one of them. Okay, so this is why we sort of, if you remember the motivation that we were giving here, we want to go from one curve to another curve by a bunch of intersection patterns. If you start with one boundary curve and end with curve which is not that boundary curve, you cannot go from one point to another point no matter what intersection property you use. The only curve that hits a boundary curve is itself. That's it. And that it's also like its geometric intersection number with any other curve is 0. You cannot do much. So that's the reason we put this essential part, and then edges. Well, remember this is where we started. We wanted this intersection number to be 1. Well, this is fairly complicated. So rather than just doing intersection number 1, we start with intersection number 0. Just take disjoint, the easiest one, and then we will increase the intersection number. Okay. So so let me write it in this terminology. There is an edge between two vertices A and B. If so, A and B, remember, are isotopy classes of simple closed curve. Now these are the vertices. So you take two vertices, one A and one B. So A is an isotopy class, B is an isotopy class, A and B are simple closed curve. Then there is an edge if this is 0. Okay. Is the question clear? Is the sorry, not the question. The description clear? So this is, so far I have just defined a graph. I haven't defined a complex. So if you want to define the simplicial complex, so a k plus 1 simplex it's a collection of k simplex. K simplex is a collection of k plus 1 vertices. That means k plus 1 collection of simple isotopy classes of simple closed curve such that I of Cij is equal to 0 for all I. So in other words, the K simplex is actually K plus 1 collection of disjoint closed curves. Okay. So this is a simplicial complex. This is called curve complex. Any questions? Any doubts about the definition? So if you look at the one simplex, it is generated by vertices and edges. So vertices are simple closed curve and edges are so what are the examples? So let me see what are the examples. So first of all, if you look at here, the vertices are isotopic classes of simple closed curve. So if you take a surface of genus G greater than equal to 2, no matter what the boundary components or functions are, you have infinitely many simple closed curve, isotopic classes of simple closed curve. So number of vertices is always infinite. This is an infinite dimensional simplicial complex to begin with. That's the first thing to keep in mind. This is an infinite dimensional simplicial complex. Second thing is each vertex has infinite degree. Because what happens is if you take a simple closed curve, so if your genus is sufficiently large, let's say genus G greater than equal to 3, if you take a simple closed curve, if you cut along that, you're going to get two surfaces, and each of them will have infinitely many simple closed curves. So therefore, each vertex meets with infinitely many other vertices. There are infinitely many edges at each vertex. So each vertex has infinite degree. So this complex is not even locally finite. So this is a widely complicated object. Okay. So here are the sort of some of the examples. So this will be a vertex. This will be a vertex. And this will give you a vertex. Okay. Now, if you look at the K simplex, this is a maximum collection of isotopic classes of simple closed curves which are pairwise disjoint. This has a name. Have we already seen this in this course? What is the collection of maximum collection of isotopic classes of simple closed curves which are pairwise disjoint?
Multi-curves.
This is a multi-curve, but this maximum term gives you some other information. It is
Band decomposition.
It is pants. It's actually pants decomposition. Filling is different. See, filling, what you want is each of them to be disk. This is telling you. So this is the picture. If you look at this picture, this is a pants decomposition of the surface. Okay. So the K simplex is actually, so first of all, every K simplex comes from a multicurve, K multicurve, and the maximum K simplex, so the maximum dimension of this simplicial complex, the maximum dimension of a cell is actually the number of pants. It actually comes from pants decomposition. So its maximum simplices are nothing but pants decomposition. So this curve is this simplicial complex is actually much more interesting than it comes to your mind when you first see the definition. Okay, so these are things you should keep in mind. This is an infinite dimensional complex. Infinite dimensional. Okay, so let me not say that. This is a finite dimensional, infinite simplicial complex. Okay, so let me write this down. This is finite dimensional, meaning that the highest dimension of a simplex is the number of Planck's curves. Okay, infinite simplicial complex. And each vertex has infinite degrees. So this is not even locally finite. Okay. Okay. Yeah.
So if you consider this genus 2 surface, and there you have then maximum collection of disjoint simple closed curves, right?
Right.
Some maximum collection.
Right.
So you are saying if we consider G greater than or equal to 3, then it will be infinite dimensional or what?
No. It will not be infinite dimension. It is always finite dimension.
For any G.
For any G, it will always be finite dimension. Because if you take any G, what's the maximum dimension? So what is it? So let me clarify this. What do I mean by the dimension of a simplicial complex? The dimension of a simplicial complex is the dimension, highest dimension of a simplex. Is that clear?
Yeah, that's fine. So
Okay.
my point is, if I consider a curve, suppose if you consider any simply closed curve,
right,
and then it gets round around some hole or something. So
that can be happening.
So now I want to rotate again. let's say it
Okay.
rounds around that n times, then I want to consider n plus 1 times, and then I
Ah,
want
but
plus 2
yeah,
times.
but first
But
of all,
they are all in distinct isotopic class, right?
right, but they will intersect each other.
I see. Okay.
So if you take this curve, so if you look at this picture, I think around here, there is a definition of yeah. This green curve, this hits this green curve actually.
Yes, yes. Okay, that
So
will.
the moment you take it, yeah. So it won't be disjoint. Will hit it.
Yeah, yeah, got the point. Okay.
So if you so the easiest way to say that to see this is a finite dimensional is look at this definition. You want a collection of simple closed curves, each of which is pairwise disjoint. So what you do is every time you have a curve, cut it, and you get another surface. Look at that surface. Take another curve which is disjoint from it, cut it. Each time you cut, you will reduce the genus by one, or the bound. So either you make the bound number of connected components smaller, that will reduce the genus, or if you split it into two parts, each of them will have lesser complexity. So cutting the curve, cutting the surface along curve, reduce the complexity, and the lowest complex surface that you will obtain is a pair of times. So ultimately, this is always finite. Okay. Okay. Any other questions? Okay. A few points that I would like to make is this. So yeah. So the first thing is, so first thing first. Let's just simply say this. So if you take any f which comes from mapping class 2, then if you add f, then if A belongs to a vertex of if A is a vertex. Okay, let me denote it something. So let me use the notation C of S. Okay, so this is the notation I'm going to use for curve complex. So suppose I take A, which is a vertex. A is a vertex in the curve complex. Okay, so it's isotopic class of simple closed curve. So then FA is also a vertex. Because if you take a mapping class, yeah, that is correct.
Can you give some motivation from this picture? Why is this of infinite diameter, this curve complex?
Infinite diameter.
Yeah, that means, I mean, if you put the natural metric coming from Euclidean.
It is not of infinite diameter.
Because, okay, it is not of infinite diameter.
Yeah,
no, I think it is not. It is it?
Yeah, I think, yeah.
It is infinite diameter. Okay, then that might be. I'm not sure why it is. Do you know any proof of it? Yeah.
So I don't know the proof, but it is of infinite diameter. Otherwise, I mean.
Okay. So let me see.
So then it will be finite complex, right?
You are right. You are right. You are right. It is not of finite diameter. Right. Right. You are right. You are right. It cannot be of infinite. It is of infinite diameter. Right. But how do I prove it's an infinite diameter? So I have to find a sequence of curves.
So for any n, you can have two curves, the section number n, right?
Yeah, but that won't prove that they are in distance in curve complex. I mean, the easiest example is if you look at so look at this curve. I think this is example. So if you look at this curve, so this two curves, geometric intersection number 2, right?
Correct. So what is the length in the curve complex?
So here the length is it? Yeah. So here the length is 2, but let's say if I do this again, so then.
So I can
Right. So this is
So,
No, so this is the argument. So this is the argument. So here is the thing. I can tell you. Yeah.
maybe
So
you have written earlier somewhere that.
no. So here let me give you something. So take this curve, which goes like 5 or 6 times or something, and then you come back here. Okay.
Is this a simple
Or,
closed curve? I don't.
which one is not? I'm just taking den twist along this.
Okay.
So let me see if I can go back.
Oh, you have written that thing earlier, right? Intersection number n.
Hmm.
The chain kind of thing.
That is for non-separating simple closed curve. And this is where I am taking the geometric intersection number to be 1, not 0.
But you can get 0 also, right? So instead of
No, but the question, so the statement you are saying is, if two curves are geometric intersection number n, their distance is n in the curve complex. That thing, I don't think that
yeah,
is true.
maybe some function of n which tends to infinity.
That is true. That might be, yeah, that's what I was thinking. So can I put a lower bound in terms of n? You're right. So that if I can prove that, then that will be infinite. But let me see. So why do we have the dimension is infinite? So, what is so I have to think about it. I have to think why it is infinite diameter. Yeah, I will check about. I will check it. I will discuss it in tutorial. Yeah, I will have it.
Yeah.
I remember. Yeah, you're right. You're right. I made the false statement. It is of infinite. It is of infinite diameter. I have to check. Yeah, I will look at it. Yeah. So, thanks. Okay. So yeah. So any other questions? Okay. So we have this mapping class group element F, and we have seen that if A is a vertex, that means an isotropic class of simple closed curve, then FA is also a vertex, an isotropic class of simple closed curve, right? Now, if A and B has geometric intersection number 1, then F is a homeomorphism. Therefore, FA and FB also has, 0. 0, then this is also 0. So edges goes to edges. So F takes vertices to vertices, edges to edges, and this is also true. If C0 to CK is a collection of disjoint simple closed curves, then their images are also going to be a collection of disjoint simple closed curves. In other words, every element of mapping class group takes a K simplex to a K simplex in the curve complex. So mapping class group of F acts on curve complex simplicially, meaning it takes simplex to simplex. Okay. So we have seen one such example where we have seen one example of a space on which the mapping class group acts, namely curve complex. So on curve complex, the mapping class group acts. Okay. So this is sort of again in terms of what I was talking about in Milner-Schwarz lemma. Let me go back to the first slide if I have it. Yeah. Right. Where is this? Okay, I haven't written it down. Anyway, so I haven't written it down. Let me say this out loud. So we got one space on which our group acts. So if we are lucky enough, and if we quotient it by this group, and the quotient has some kind of finite property, then we may assume that, okay, so then we may try to prove that, okay, these things are good enough and the quotient is finite. So the map, the group has some kind of finite property, either it's finitely represented or finitely generated or some such property. Now, in this generality, this is not again quite true. We cannot directly prove most of the result. So what we are going to do, we are going to modify this according to our need. Okay. So first of all, we have to prove that this space is connected. So remember, this was the motivation. The motivation was it acts on a space which was connected, and if we can prove the modified space is connected, then we will be able to prove that it is generated by dent. So the first step here, so but this is a different complex, this is a different graph, this is a different complex. This one we have just defined, this is a different complex or complex. So first we are going to prove that this is connected, and then we will modify this to go back to our original one where we want intersection number to be 1. Okay. So first let me prove that this curve complex is connected. So let me write down this result. So this is lemma of theorem or something. So I need one technical condition. I need one thing. Let me check the technical condition. Yeah. So if 3g plus n or 3 plus yeah, g plus n is greater than equal to 5, then this is connected. Okay. So the reason why this is, I mean, sort of we need a modification is the following. If you, so the first thing is, if you look at a pair of bands, there are no essential simple closed curve. So the curve complex is vacant. There is nothing there. Okay. Now, if you look at let's say torus with one boundary puncture. Okay. So then what happens is, if you look at this curve, no matter which other essential simple closed curve you consider, it will also always hit this curve. Okay. So this curve will be disjoint from any other curve. This vertex will be disjoint from any other vertex. No matter which vertex you consider, this vertex will be disjoint from any other vertex. So this curve complex for torus with one boundary components or torus with one function is simply not connected, not even connected. Okay. So lower genus surface, we have these two problems. Either it can be a bunch of simple vertices, or it might be trivial, or even if it is non-trivial in this kind of cases, it might not even be connected. Okay. Is the example clear? That if you take a torus with one boundary or one function.
Sir, can you repeat this thing?
Yeah. So let me say, okay, let me state this thing clearly. So consider S13, which is torus with one boundary or one function, doesn't matter. In curve complex, you don't care. Okay. Now, if you take it, if you take this curve, so let's consider the curve C here. Okay. So consider this curve C belongs to vertex vertices. So let me just write it out. Let C be a vertex of curve complexes. Okay. So this is C. This is isotopic class of simple closed curve. Can you see the screen?
No, sir. It's
okay.
There is a lag.
Okay, let me just check.
So also I missed the motivation. So why we need to be vertex to be essential curve? Okay,
so we need the vertex to be essential curve because of a simple reason. The point is, if you take non-essential, so let us remember what is the proof that we are trying to prove. That we are trying to show that the mapping class group is generated by the product of dent twist, right? Now what happens is, if you look at dent twist along the boundary curve, you cannot generate it using any other dent. Or another way to say this thing is, let me just show. Let me share the computer. So if you look at this argument, remember this argument, we want to go from A to FA using this intersection pattern, right? We want to go from between two curves. We want to use a bunch of curves so that we can go from one curve to another curve just by using some intersection pattern. This is okay?
Yes, sir.
Okay. Now, the point is, remember this relation. Now, the point is, if you take two boundary curves, you consider them as vertices of curve complex, you cannot go from one to another using this relation. Because no matter what curve you choose here, its geometric intersection with boundary curve will be 0.
Okay.
So if I focus on this relation, I cannot go from one boundary curve to another boundary curve.
So that's why I asked this. So if I include essentially in case of torus with one boundary curve, that will be graph will be connected.
Right. Exactly. So here, exactly. So you're right. So let me come back to this one. So if you look at torus with one boundary component, if you look at this vertex C, then C is a disconnected vertex. Meaning there is no other vertex which has an edge with C. Because if there is any other curve on the surface, any other essential closed curve, it always hits C. So this is because for any other isotopy class of simple closed curve B, C of B is non-zero. Okay. Is this clear? Why with surface with torus with one boundary puncture, this is singular vertex, this is a disconnected vertex. Any questions? Okay. So we got 2 points here. First, if our surface is complicated enough, then this is connected. But the problem is in a lower genus surface, these things are not connected. And the other problem is, as we mentioned, that we cannot go from boundary to boundary, so we have to consider essential closed curves. Okay. So just to avoid this thing, just to include low genus surface, what we can do is, rather than taking intersection number to be 0, we can take intersection number to be 1. Rather than taking intersection number to be 0, we can take simply intersection number to be 1. And again, this makes sense. You will get another complex. But then we need to have some extra assumptions. Okay. Why do we need the extra assumptions? And the reason we want to have this extra assumption is to prove this theorem. So first, we will prove this theorem that if Cg plus n is greater than or equal to 5 in curve complex, then the curve complex is connected. Then we will modify the curve complex a little bit. And then we will show that the modified curve complex is also connected. Then we modified that complexes further to make it suitable for our proof, for our genus. Is this clear? Any questions? Okay, so I will stop here and then we will start our discussion in the tutorial session. We'll continue this discussion. I thought I would be able to prove more, but then yeah, in the discussion session I will explain these things again. Yeah. So any questions? So Somo already gave a link in the chat box where you have a proof which is which has of infinite diameter. Thanks, Somo. I will have a look at it.
Yeah, any other question? Okay, so Arpan, thank you.
Yeah.
So,
So what time are we joining?
so again, we start at 11:30. So don't, you may not leave this meeting.
Okay.
It's
So
up to,
this.
or
Okay, sure.
you can also. So I'm not